Hey everybody, you know the deal. I'm trying to get us through our work and energy unit, so I want to help us through one of our review packets. So we're finding the Unit 5 review packet, looks something like this, and I will try to be as brief as possible. Feel free to skip ahead to the problems you got stuck on. So the steps for this are you try it first, then check the answer key, then watch this video if you want more detail on how a certain problem is done. Okay, that being said, let's do this. So, if the sign of work is negative, that means some component of force is trying to slow you down. If it was in the same direction, then it would speed you up, and work is positive. Think like if the force and distance are working together, it adds energy to the system. If they're perpendicular, like how normal force normally is, then the work done is zero because it's not moving the object in the same direction. So it's not B or D that both deal with perpendicular. It's got to be in the direction opposite displacement. As long as I have some portion of the force acting backward, like in this case, as long as I have some portion of the force acting backward, it has a component that is negative, in this case the x component of this force is negative, then you will lose energy, the work will become negative. 2 is kind of tricky. I love it. 2's answer is A. All of the other choices have no work. When a planet orbits the sun, it actually doesn't do work at all. I want you to think about the planet as going a circular orbit around the sun. That means the force it goes is towards the center of the solar system, towards the sun. The direction it travels is down, and that always makes a 90-degree angle. Plus, it doesn't change the speed. The planet orbits the sun at the same speed the whole time because the distance and force are perpendicular. So we can kind of ignore that. Not B. For C, it prevents the sled from sliding. It doesn't move. If distance is 0, work is 0. And finally, gravity is perpendicular to the direction that a bowling ball moves down the lane. Since it's 90 degrees, same thing as the force due to gravity and distance in an orbit, 90 degrees, 0 work. So, for number 3, when friction does negative work on a moving car, that's because friction is from an external object, that is, the ground. It's not going to transform into gravitational potential energy because that would be friction drags the car up a hill. That doesn't make sense. That means instead what's going to happen is there's positive kinetic energy of the car to start, negative work occurs, and there's less kinetic energy than original. Kinetic energy decreases. The kinetic energy in this case is transforming out of the system. Think of like the mechanical energies are just PEG, PES, and kinetic. Thermal energy would be a non-mechanical energy. So I suppose if you wanted to, you could call thermal or internal energy as this loss. So if I had 10 joules of kinetic energy and I only ended up with 2 joules at the end, that must mean friction turns the kinetic energy into heat. 8 joules of heat. Heat is usually written as E internal, because think of it as like it's the internal vibrations of the atoms. Right? Or thermal. So how would we write this? Maybe like ET for thermal, something like that. Since thermal energy is non-mechanical, it's normally not included in a diagram like the one we've been doing. Okay, I see a graph. I know that there are certain things I can do with a graph. I can take the slope, I can take the area, or I can read the y-axis. In this case, this is referring to work with a force and distance graph. I want to be looking at area. So, I did this beforehand. I took the area from 0 to 5, and that got 12.5 joules. Then I took the area from 5 to 8, and that was only 7.5 joules. I did the area by doing 1/2 base times height of each side of this. So I see that it does more work from 0 to 5 meters than it does from 5 to 8. The total work would be adding them up, however, would be the work done by this whole triangle. And that's where I got the 20. Was the net work would be adding 12.5 plus 7.5 to give me 20 total. And since this problem is indicating that that 20 joules goes to kinetic energy, think of it as like you start with 0 kinetic energy. You do 20 joules of work. Well, you should end up with 20 joules of kinetic energy at the end. So, to find the speed, anytime I want to find a speed in this unit, think to yourself, speeds are from kinetic energy. So I'm going to write down my kinetic energy equation, the 1/2 mv squared. 20 is equal to 1/2 times 2 times v squared. If you're wondering where the 2 comes from, it's a 2 kilogram object. So I'm going to put m is 2. Therefore, 20 equals v squared, v equals square root of 20, and that's where I got my answer of A, 4.5. Finally, power. Power is work divided out by the time it takes the work to be done. So that's not bad. 20 joules, 10 seconds. Okay, my bad on this. If you were wondering where the time is in this, I accidentally put it in part C. I probably should have put it in the header for this section. So it reads like a 2 kilogram object is at rest, blah, 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 but takes 10 seconds to move. But I put the 10 seconds in C. Take that 10 seconds in C and apply it to 7. That's what's up with that. That's where I'm getting my 2 watts from. It's work divided by time. The time it takes the work to be done. Math. Okay. So, originally, when we did gravitational force in orbit, we talked about how there's this approximation. You could, like I did in number 2, say that as a planet goes around the sun, it makes a perfect circle with the uniform, the same speed everywhere. So, since the radius is equal everywhere, the speed is the same everywhere. And that's kind of nice because it makes our lives easy. But in real life, that's not really what happens. And we get situations like this. It turns out, in January, we're actually going to be closer to the sun than we are in July. If you're wondering why does that mean it's colder in January, it's because the northern hemisphere is tilted away from the sun in January and towards the sun in July, and therefore it's a little bit warmer in July than it is in January. So, what's up with this one? This is asking you to figure out where do you move fastest. Where you move fastest is when you're closest to the sun. Maximum kinetic energy then is B, January. When I'm closest to the sun, I move faster. And if you're wondering why that is, guys, remember back to Unit 3. The closer you are to the sun, the more gravity acts on you. The more gravity acts on you, the faster you travel. This is Kepler's second law, the law of equal areas and equal times. When I'm in January, the time it takes to travel this distance is much, much smaller. When I'm closer to the sun, gravitational force is bigger. So when I am at the perihelion, I go faster. When I'm at the aphelion, I go slower. Slow. The other way you can think of it is when I'm at the aphelion, I'm a larger distance away from the sun. I know that's not particularly a height, but you can think of it like a height in the MGH equation. The farther you are away from the sun, the more gravitational potential energy you have. Just like if you were a rock that's higher up away from the Earth. You'd have more gravitational potential because you're farther from the object, the big, massive object that's creating the gravitational field that you're in. So with these two objects, the farther you are away from the central mass, the more gravitational potential energy you have. Which is why there's more gravitational potential energy in July, because you're farther. But the total mechanical energy should be equal everywhere, because our system is going to be the Earth-Sun system, and there's no other objects acting on it. It's not like the Earth-Sun system and asteroids impacting the Earth. There's no external objects, there go no external forces, therefore total mechanical energy is all the same. In fact, I don't even know why I put in this column, because if they're all the same and there's no other options, that column's just there for funsies. Oh well. So, number 9 I thought was kind of tricky. Number 9, there is no work done because energy is conserved. As mentioned in 8, total mechanical energy is all equal everywhere. Therefore, there's no external forces, therefore no net work. A would be true if you defined your system to be Earth only. But then it would be like the sun is not part of this orbit, and that's just not a sensible choice. But it's definitely not C. The sun definitely doesn't do negative work on the Earth because as it's going from January to July, it's actually gravitational potential energy is increasing. So it can't be that. 10. 10 through 12 refer to power. Power is work divided by time. But to get the work in this problem, I'm going to use the fact that it gains gravitational potential energy. That angle is actually irrelevant. It's there to be extraneous or to distract you from the problem at hand. There's constant kinetic energy because there's constant speed. So if I'm picturing my energy bar graphs here, whatever I choose for kinetic energy, it's going to be the same before and after. So it's kind of irrelevant. But it does go from zero gravitational potential energy to some positive gravitational potential energy. The work done in this system must have been to add gravitational potential energy. So, if I could calculate this gravitational potential energy highlighted here in blue, then I could get the work. And using the work, I could get the power. So, it's a 300 kilogram ski lift raised 50 meters into the air. That means my gravitational potential energy would be mgh. My gravitational potential energy would be 300 times 9.8 times 50. And so it's going to add work to the system. A whole bunch of work. 147,000 joules of work is done. So in this case, the work equals potential energy. And since power is work divided by time, I would take my power, work time, so I would take my 147,000 joules divided by 120 seconds for 2 minutes. It's 120 seconds of time. And that gets me 1,225 joules. I'm going to pick the closest number to 1,225, and that is B. I'm going to guess the discrepancy between the 1,225 and 1,250 is coming from the fact that you could estimate 9.8 as 10, which would make this 150,000 divided by 120 to get 1,500. Okay, power is work divided by time. So if you took twice as long to do the same amount of work, that would be D. Power would be halved. If I took twice as much time to run a mile, I have to exert less power. I do the same amount of work, so it can't be A, and it can't be C. So choosing between B and D, I don't exert more power to run slower. I must exert less power to run slower. For 12, the energy transformations then, it has constant kinetic energy. So I'm looking for this key term. The kinetic energy before and after should have been the same number. And it should be increasing gravitational potential energy. So 12B. Okay, the next few problems are all proportions, graphs. Just can we understand gravitational potential energy? So, for problem 13, please just do this one out mathematically. Gravitational potential energy depends on mass, gravitational field, and height. Since you're in identical gravitational fields, whichever one has the greater product of mass times height has the greater potential energy. So, 3 times 4 times 9.8 equals 2 times 6 times 9.8, C. For 14, I've got a ball, and it becomes a projectile. Before the ball is struck is A, so it has no gravitational potential energy. Just after it's struck is B. It's right above the ground, it's going very, very fast, but it's still really close to the ground. Height is small, gravitational potential energy is small. C is at the apex of motion, where you're going slow, but your height is big. And the bigger the height, the bigger your gravitational potential energy. Height goes up, gravitational potential energy goes up. And actually, when the ball is in the hole at D, it's actually negative potential energy, so not that. So, we know from these three problems that as height goes up, gravitational potential energy goes up. This is direct relationship. There's no squares, there's no like square roots here. So this graph should look like A. Number 1, a direct relationship, linear and going through the origin. Okay, 16, 17, 18, and 19 do the same study, but with kinetic energy instead of gravitational potential. When I do proportions, I'm going to take into account things that are squared as more important than things that are just linear. That means mass is less important to doing the proportions than speed is. In my head, I'm really only choosing between C and D because speed is a squared quantity and mass isn't. So the fact that these two have more mass is irrelevant because those two have more speed. So it's not A, it's not B. So let's compare them. I do this out with proportions, but if you wanted to call M equals 1 and V equals 1 and just like get a real number, you could totally do that. But I'm going to do this with proportions. So the kinetic energy for C is 1/2 2m 3v squared. 1/2 times 2 is m, but 3v squared is 9v squared when I distribute properly. And this is 9mv squared for C. D is 1/2 m 4v squared. So it's 1/2 m times 16v squared when I distribute the squared to the 4 and the v. And that only gives me 8mv squared. So C has more kinetic energy than D. 17, literally the same type of problem. I'm trying to take my kinetic energy and compare it. So in the original case, I've got a mass m, velocity v. Now I have a smaller massed object, so 1/2 m, and the velocity is doubled to 2v. But it's 2v squared, where the square acts on both the 2 and the v. So this gets me 1/4 times m times 4v squared, or mv squared. So if I compare original to new, I now have twice as much the kinetic energy. Let's see. If you really wanted to try this out differently, what I would suggest, pick m equals 1, pick v equals 1, and then when you do this out, you would get a kinetic energy of 0.5 to start, compared to a kinetic energy of 1 joule at the end. You double your kinetic energy, so twice as much as before. Wow, guys, I managed to write like 3 in a row of the same type of problem. This is just slightly different because it deals with stopping distance. Okay? So think of stopping distance as if you need to take your kinetic energy and apply work, some negative amount of work, to come to rest, 0 kinetic energy. That must mean the more kinetic energy you have, the more work is done. Since work is equal to Fd cosine theta, the more work friction needs to do to stop your car, the more distance it takes to do so. Whatever portion kinetic energy changes by, distance also changes by. So, oh gosh, doing another proportions problem. Ms. Pasega, why would you do this? So, if I triple the velocity, I nanuple. That sounds funny. I have 9 times the kinetic energy as before. So if I have 9 times the kinetic energy, it will take 9 times the stopping distance, d. That's why it is so important, guys, that when you drive, you keep your speed under control. The difference between 10 miles and 30 miles an hour in a collision is actually 9 times the crush distance. If you're using your brakes, that's not a big deal. That means I can, brake in a 9 times shorter distance. But if that means that my car is going to crush 9 times farther, that could start impeding on like the safety cage and where you reside in your car. So by all means, travel slower if you can. Last one having to do with kinetic energy. Literally 16, 17, 18, all we're dealing with proportions of kinetic energy. And the important proportion here was that as velocity increased, because velocity is squared, kinetic energy increased also. That squared relationship means if I were to graph kinetic energy is 1/2 mv squared, as y is kinetic energy, we're going to ignore the slope for a second. This would look like y is x squared, it's a. The squared relationship makes it look like a squared function. Not a square root, not direct, not horizontal, which would be no relationship. We definitely know that's not correct. This would mean that as speed changed, your kinetic energy stayed constant. Not that. 20 has really tricky wording. Not a huge fan of how I worded that. I'm going to change it to make it better for next year. But on this, your procedure when you originally did the lab with the multicolored springs was you did something along the lines of measuring the elongation lengths, not the equilibrium lengths. It can't be A or D, because A says you would put equilibrium length here, but any one spring has the same equilibrium length. They're about 25 centimeters and they stay 25 centimeters. You would just have like one data point, so it's not A or D. And the only difference between B and C is C gives me a force versus displacement graph. B would give me a mass versus displacement graph. You guys that did mass as a procedure should have changed your mass to force, and most of you did. But that is a common misconception. It's not mass versus distance, it's force versus distance. So I can't have B as my solution. Okay. So, 21. Spring constant of the spring is determined by reading the slope. Without doing any math, I know it's not y-axis area under the curve or multiplying force times distance. That's not even the same problem. That would be like work. That's not what we got. So this would be 6 divided by 10, so 0.6. Neato. So 22. You can do this out mathematically if you want. In this case, if the spring is stretched to 5 centimeters, you could go take the area under the curve and figure out how much energy that stores. And then notice that doubling the displacement gives you 4 times your original energy, so this is the original. This would be twice as big, 3 times as big, 4 times as big area. Or you could notice that, hey, this is a proportion because PES is 1/2 kx squared for the same spring. If you double x, you quadruple the energy. You can get that from proportions or from the graph, where I see that the energy gets 4 times as big because the area gets 4 times as big. Now on to the problem. Gravitational potential energy is biggest when you're highest from the ground. That puts A, D, C, B, and E. B and E are equal because they're both on the ground. And what I'm thinking of for a solution here is this is true because as height goes up, gravitational potential energy goes up. So A is the highest up. A has the most gravitational potential energy. B, kinetic energy. If total energy is constant and is equal to kinetic plus gravitational, that must mean the items that have the largest kinetic energy must have the least gravitational potential energy. To me, this makes sense because when I'm on a roller coaster, I'm going fastest when I'm near the ground. So B and E, ignoring friction, are nearest the ground, would be going fastest. Then C, then D, then A. But if friction were included, then at B, you would have all kinetic energy. There would be some sort of negative work done by friction because the ground or the ramp would be the external object and the friction would be the external force. You'd end up with less kinetic energy at E because it would have turned into thermal, which you could write as EINT for internal. So if you had, 100 kinetic energy at B and only 230 at E, that would mean that 70 was lost to friction and turned to heat. Heat is not normally drawn into the diagram because it's not one of those 3 mechanical forms of energy. And I see that you missed that because I drew it off screen. Okay, so this problem, 24, is exactly like the work in Power Lab we did in class. One of the methods we were using to find work done by you as you did push-ups and squats and ran up and down the stairs was to set your work equal to the gravitational potential energy you gained. When Lucy is doing pull-ups here, she gains mgh worth of energy for each pull-up she does. So I'm doing 40 times 9.8 times 0.25 to get me 98 joules per pull-up, which for 10 pull-ups means 980 joules total. And if you have trouble picturing like where is this energy coming from, think for each pull-up. She starts with no gravitational potential energy, applies work on herself, and ends up with 98 joules of gravitational potential energy at the end. Work is positive because she is adding energy to the system with the applied force. So, power. Power is work divided out by the time it takes the work to be done. At least this one's easy because it's only 20 seconds. So that gives her 49 watts of power. And if she took less time, that means power is bigger. She has to go at a faster rate to change energy. So I would say the power she generates increases for the same amount of work. She's still got to do the pull-up, so she's still got to put in the work. She just needs to do it faster, so she needs more power to do so. On the answer key, I actually drew this handy graph here. So if this is time versus potential energy, she normally would take 20 seconds. And to be fair, like this is a lot. This is a lot. I couldn't do this many pull-ups probably ever in my life. And here she is just like doing the pull-ups in 20 seconds. Originally, she does all the same amount of work, but in 20 seconds. If she does it in 10 seconds, this is steeper. So this line at the top indicates same gravitational potential energy, same work, but it's steeper, so more power. She's like playing this on beast mode, more power for the same work. Okay, number 25 is going to take us a second because this was that problem we did in class together. We did like problems 4 and 5 of that packet. I made a video for a similar one. But unlike some of the other ones, a problem like this requires a lot of steps and some review. So, I know you know how to do this. We've got 4 forces acting on this wagon. Kid pulls up, applied force, normal force from the ground supporting it, gravity, and friction. We know the gravitational force is 10 times 9.8 to be 98 newtons down. And this problem is nice because before, on the homework, I didn't give you the sub-step of resolving the applied force into components. So, just for reference, this equation is on the bottom of the Unit 1 on your equation sheet. F(a)x of a vector versus F(a)y of a vector. I'm going to skip and just do F(a)y, though in the actual answer key I do both, for the sake of time. So F(a)y is taking the magnitude of the applied force times sine of the angle. So 50 newtons sine 37 is equal to 30 newtons up. This means it falls under this case from my previous video. If the child is pulling upward, then the normal force and applied force work together to cancel out gravity. So in our case, normal force goes up, applied force goes up, gravity pulls down. So the normal force has to cancel out the 98 newtons, but it gets 30 newtons of help from the girl and her applied force upward. Since the normal force plus F(a)y equals Fg, that means something along the lines of Fn plus 30 equals 98, Fn equals 68 newtons up. So then the friction force is mu times Fn. This equation is on the bottom of the Unit 2 equation sheet, section of the equation sheet. 0.2 times 68 gives me just 13.6 newtons left. This problem is also nicer than the ones I gave for homework because I kind of hint to you that the work done by normal and gravity is 0 because I only have you calculate the two that actually give non-zero values for work. The applied force does positive work because when you do FAD cosine theta, you get something along the lines of 50 times 5 times cosine 37, or adds 200 joules of energy to the system. And in my head, it's because I'm drawing FA here and distance to the right, so that my angle is 37 between those two. Whereas for friction, friction goes left, distance goes right, making this 180 degrees. That makes the work done by friction negative, as per usual, or 13.6 times 5 cos 180, and it takes out 68 joules of energy from the system and turns it to heat. So how I would draw this. Thing to be careful of here. This initial velocity of 3 meters per second, it means it has initial kinetic energy. So I gotta find that first. Kinetic energy is 1/2 mv squared. So in this case, 1/2 times 10 times 3 squared. That's 5 times 9, or 45 joules to start. If I choose my scale to be 20 joules per division, that means I have 45 joules to start here. I add a net work of 177. Hold on, that doesn't sound right. Nope, I got it. Here it is. Work in this case is 200 minus 68. So my work is positive 132. There we go. Work adds 132 joules. So I would draw this here. There we go. Where's the 177 coming from? Is that my total kinetic energy now is 45 plus 132 for 177 joules kinetic energy total at the end. Yes, good at this. So I would explain my choices of scale. I chose my 20 joule scale so that I could fit 177 joules onto a 9-section chart. I have 45 joules of kinetic energy to start, with 132 joules of work done to make 177 total. Final velocity then. Whenever I see something with velocity in this unit, I'm going to write down KE equals 1/2 mv squared, so that I can just substitute and solve for speed easily. So, to solve for v, divide by 5 on both sides and take a square root. This gives me 5.95 meters per second final speed. So it was originally going 3 meters per second. Now it's going almost 6 meters per second because work was added to the system. Okay, so almost done. 2 left. This is another quantitative conservation of energy problem. In this problem, I want to find total mechanical energy, and I can find it at either point A, point B, or point C, but whichever point I find it for, it's going to be the same number at all 3. So in my head, what I'm taking off is I need to know the speed and height at each location. At A, I know the speed and height. At B, I only know the speed, so I have to go calculate the height later. At C, I know the height is 0, but I don't know the speed. So I'm going to calculate that later. The only one of these points I know both things for is A. So when I go calculate the total mechanical energy, I want to get the kinetic energy at A plus the potential energy at A to get the total energy. So at A, I take the mass of the ball times the velocity of 12 squared to get 7.2 joules of kinetic energy. I get the gravitational potential energy, because it's at 15 meters initially, to be 14.7. And that gives me a total of 21.9 joules. Funny symbol thing. If you were looking at this and we were like, ugh, what is ugh? Well, for other types of physics, instead of using PEG and PES, they actually use UG and US. If you really want to know, it's because the spring potential energy graph looks something like this when you graph it at X versus US. And since it looks like a U, they made the symbol a U. True story. We're going to call it PEG, PES, because that will be similar to what we did in class. So if you're wondering what's up with that, that's just a slightly different naming convention for the symbols. So I'm going to pick my scale. I picked my scale to be 4 units each because I'm trying to fit a total of 21.9 joules into a 9 scale. So that means I have 7.2 joules kinetic at point A plus 14.7 of gravitational potential energy at point A with 0 spring. At point B, it's going to still have 0 spring, C0 spring, C0 potential. But before I can fill that out, I need to find my extra things. I do know that at point B, the kinetic energy is a calculable quantity. At point B, the kinetic energy is 1/2 mv squared. So 1/2, in this case, 0.1, v is 5 squared, gives me 1.25 joules of kinetic energy at B. So if there's 1.5 joules or 1.25 joules of kinetic energy at B, and they need to add up to 21.9 total, well, I can subtract to find that. That means the potential energy at B is 21.9 total minus 1.25 of kinetic to give me 20.65 joules gravitational potential energy at B. So that's around here. How to find the height at B then? If the gravitational potential energy is equal to mgh, and there's 20.65 joules of it, I can find the height by dividing by 0.98 to both sides, giving me 21.1 meters. Now let's just check and see if this makes sense, okay? It started at 15 meters, and it went higher up in the air to 21.1. That makes sense to me. B should be higher than A, and B should be slower than A. That's cool. C should be lower but faster than either B or A. Because at C, all the kinetic energy is equal to 21.9, so that's around here-ish. Because it's not gravitational and it's not spring, all 21.9 total must be kinetic. And that allows me to find the final speed. 21.9 equals 1/2 0.1 v squared to find the final speed of like 20.9 meters per second. It should be going faster than A or B because it's lower towards the ground than A and B. But if the ball were thrown straight up, it would travel upwards, slow down and stop entirely at the top. Point B then would have all gravitational potential with no kinetic. It still would have the same initial condition as A though, so the total mechanical energy would still equal that 21.9 total, but would all be gravitational potential. So let's solve this for height and see if it's higher or lower. If it were shot directly straight up, then the gravitational potential energy would give us a height of 0.1 times 9.8. We're going to divide by h. Of 22.3 meters. This is higher in the air than it was originally. Right? Originally, the height was 21.1. Now it's 22.3. It is higher than it was before. And really, what's going on here, guys, is that at B originally, I don't know why it got so dark for a second. At B originally, it had kinetic energy, which took away from its potential energy. Now that it's thrown straight up in the air, it full stops at the top. So now there's no kinetic energy, and it has all potential energy. Guys, we're almost done, okay? So, in this particular problem, we have 4 pictures. A is on the ground, B is at rest at the top, C is actually supposed to be moving. The arrow, I think, showed up under where this mass is, so C is moving. And D is at rest again. Okay, as long as you are self-consistent, yours can be slightly different from mine, but as long as you're self-consistent, you'll be doing fine. In A, the mass is on the table, there's no movement, it's not stretching the spring because it's not even touching the spring. Zeros across the board for A. At B though, it's not moving, the spring is unstretched, and it is above the ground. That looks like a gain in energy to me, so some positive work must have been done by an external force. The work done by the external force must be the work done by your hand intervening in this problem. So I'm going to make sure to leave my hand out of this energy flow diagram, because my hand is going to be my external object applying the external force to add work to this system. Objects in this system would be the mass and the earth, because the earth gives it gravitational potential energy. If you really wanted to, I guess you could also put the spring. I'm not going to bother though, because if the spring energy is 0 before and after, it's kind of irrelevant. Then from B to C, the hand disappears. It moves down, lowering the gravitational potential energy, starts moving, increasing the kinetic energy, and now has stretched the spring from its equilibrium position. So, if originally it had 030 for its energies, I'm still going to have 030. I'm going to be self-consistent here. And after it has less gravitational potential, it has some spring and some kinetic because it's moving above the ground and the spring is outstretched. And there's now no external forces. Hand is not touching it at all. So hand can't apply an external force. I would call this mass spring earth as my system. Now I'm including the spring because now I have spring potential energy. Ta-da! I'm going to get points from correctly labeling my system. Correctly identifying that this energy here is the same. Like those 2 pictures should be identical because it's still picture B and picture B. Okay? I would get points for noticing that the kinetic energy increases, the potential energy decreases, and the spring energy increases. Finally, from C to D. C's picture should be the same as it was just a second ago. So 1, 1, 1. Hey, 1, 1, 1. It doesn't have to be 1, 1, 1. I picked those numbers randomly because they added up to 3. You could make them like 0.25, 0.5, and some other number, the number that adds up to 3. But that is up to you. So, last picture then for D is stationary. So I need to draw kinetic energy 0. Slightly above the ground. So I made this number super duper small, like 0.25, but feel free to pick your own small number. I know you can be creative here. As long as it still adds up to 3 total. So that's 2.75 here for spring potential energy. I would get points in this for noticing that kinetic energy decreases to 0. Gravitational potential energy decreases because I get smaller. And that spring potential energy increases because the stretch distance got bigger. Still mass spring Earth as a system. Because I have a moving object, it's above the ground, and there's a spring in it, so 3 objects for 3 energies. Guys, I think we're done. And it only took me like an hour. So, good luck on your review packet. I will see you in class. Have a good weekend.